After studying this module, you shall be able to know about the other important correlation methods. Learn the concept and applications of point-biserial correlation. Learn the concept and applications of biserial correlation, and you will know to use IBM SPSS 20 for correlation coefficients. A mother wants to know if providing positive feedback on a dance performance is going to improve the child's performance on it. There are three possible results that come out of giving the feedback. Positive feedback will improve the performance, indicative of a positive relationship between the feedback and the performance. The performance would remain same and show no change, which means that providing the feedback and performance actually do not share any relationship, and the performance would decline, which would indicate that providing a feedback would actually lead to a decline on the dance performance, that is indicative of a negative relationship. The concept of correlation coefficient is invaluable to quantitative research. The Pearson's product moment correlation coefficient is a linear relationship among two continuous variables, and many a times the research data does not conform to the assumptions of linearity and continuity, and hence it is not suitable for Pearson's R. So, other measures of correlation have also been devised by the statistician. The present module discusses the statistical relationship among the variables. We shall attempt to understand the different methods in the current and the next modules. The data may be in the form of descriptive categories, non-linear and multivariate in nature. The point-biserial correlation. The concept of point-biserial correlation. What is the point-biserial correlation coefficient? The point-biserial correlation coefficient, symbolized as R subscripted by PBI, signifying point-biserial, is a statistic used to estimate the degree of relationship between a naturally occurring dichotomous nominal scale and an interval scale or ratio scale measure. For an example, we can see a researcher might want to investigate the degree of relationship between gender, that is being male or female, a naturally occurring dichotomous nominal scale, and achievement in English as a second language as measured by the score on the end of the year departmental exams, which of course would be in interval scale of measurement. Aside from the types of scales involved, the interpretation of the resulting coefficient is very similar to that for the more commonly reported Pearson's product moment correlation, sometimes referred to as Pearson's R or simply R. In brief, like the Pearson's R, the R-PBI or the point-biserial correlation can range from 0 to +1. If the two scales are related positively, that is in the same direction, and from 0 to -1 if the two scales, that is the two variables, are related negatively, that is in the opposite direction, which means increasing one variable would result with a decrease in the other variable. The higher the value of RPBI or the point-biserial correlation coefficient, the stronger is the relationship between the two variables, positive or negative depending upon the sign of the statistic obtained. The point-biserial correlation coefficient is an estimate of product moment correlation under special circumstances when certain assumptions of the linear correlation are not met and the point-biserial correlation coefficients have been are indicative in the data. A research data may comprise of continuous as well as categorically measured variables. If the categorical variable is dichotomous, then the relationship between the two variables can be established using point-biserial correlation. The term dichotomous, of course, means cut into two parts. So, if a variable can be measured in just two categories, it can be called as a dichotomous variable. An example of a dichotomous variable is gender, male or female. There is no underlying continuum between these two categories. In point-biserial correlation coefficient, that is RPB, one of the variables is categorical and dichotomous into mutually exclusive categories and the other is continuous. So, if a study involves exploring the relationship between gender and anxiety, point-biserial correlation coefficient is an appropriate measure. The anxiety is a continuous variable, whereas gender is a categorical dichotomous variable. The point-biserial correlation coefficient is useful in when the data comprises of a continuous and other dichotomous variable. The data is not suitable for Pearson's product moment correlation coefficient. The analysis of items of a test, that is in item test correlation, the point-biserial correlation is very useful. Calculation formula for point-biserial correlation coefficient. The equation 1 gives the formula that we use for the calculation of point-biserial correlation. RPB is equal to mean of P, that is MP, minus mean of Q, that is MQ, divided by the standard deviation into the under root of PQ. Let us understand this formula, what each symbol means. In the equation 1, MP and MQ are means of the two categories that need to be correlated. P is the proportion of the sample in the first group. Q is the proportion of the sample in the second group. Sigma is the standard deviation of the entire group. The calculation of point-biserial correlation coefficient using product moment formula. There is an alternative formula also for the calculation of point-biserial, and the point-biserial correlation coefficient is a product moment correlation and thus can also be calculated using the formula RPB is equal to n sigma xy minus sigma x into sigma y divided by the square root of n sigma y square minus sigma y whole square into n sigma x square minus sigma x whole square. we are going to label this equation of calculation of point biserial correlation using product moment correlation as the equation 2. So, now we have two formula for the calculation of point biserial correlation. One is given in equation 1 and the other one is given as equation 2. Let us explore the concept further and take up a numerical to calculate the point biserial correlation. Numerical application of point biserial correlation. A researcher wishes to explore if anxiety scores obtained during a task performance were related to the gender of the group being tested. The scores on anxiety test as obtained by the males and females are presented under table. The table 1, which gives the anxiety scores obtained by males, the males have been coded as 1 and obtained by females who have been coded as 0. The obtained scores are given in the column anxiety, gender. Anxiety has been coded as the X variable and gender as the Y variable. The squared values and the product of the two scores are also given and the column sums are also given at the bottom for all the subjects where the total number of subjects is, or the n is 15. We find the totals at the bottom and let us see how we can calculate the point biserial correlation. In the first, we are going to use the equation 1 for the calculation. We find the males mean to be 201 upon 9, that is 22.33. The females mean is calculated to be 122 upon 6, that is 20.33. The total mean is 323 divided by 15, as the total sample size is 15, which is 21.53. The proportion is for the males is 9 upon 15, as the number of males is 9 out of 15 and the proportion is 0.6. For the females, the proportion is Q and is calculated to be 6 upon 15 is equal to 0.4. Using equation 1, the point biserial correlation coefficient has been calculated after the application of all the numerical values obtained, and it is found to be 0.54. The same value of point biserial correlation coefficient can also be obtained using the product moment correlation formula given in equation 2. Let us see how it is done. On application and substitution of the values from the table 1 in the equation 2, we arrive at point biserial to be 15 into 201 minus 323 into 9 upon the square root of 15 into 9 minus 9 square multiplied with 15 into 7005 minus 323, and the value of point biserial turns out to be 0.54. So, with the same set of data, on application of equation 1 or equation 2, that is the two equations or methods that we discussed for the calculation of point biserial, we arrive at the same result, the point biserial correlation coefficient to be of value 0.54. So, both the equations arrive at the same result. Significance of point biserial R. The obtained value of point biserial R can be put to test against the null hypothesis. The degree of freedom n-2 can be used to find the critical value of R from the table. If the R calculated is more than R critical, then it can be taken as significant and the null hypothesis can be rejected. The biserial correlation. The concept of biserial correlation coefficient is quite similar to the point-biserial correlation only. The difference between the two pertains to the measurement of the categorical variable only. The dichotomy in the variable is not true but has an underlying continuity to it in biserial correlation. In other words, one may say that the variable in which dichotomy is assumed may be found to be continuous and normally distributed had more information been taken into account, like dividing the students into those who are graduates and those who are not. You may have two sets to be measured, the graduate students and non-graduate students. But if we delve more and we take more information from the subjects, we may arrive at the underlying continuity, that is, a small section of those students who may have attempted graduation studies but unable to complete or are in the process of accomplishing their graduation. So, the categorical variable as measured by the researcher may be dichotomous, but on probing a little further, it cannot be said to be split in two categories only of graduates and non-graduates. Rather, an arbitrary split point is created to facilitate the grouping for the purpose of research. Whenever you have such data in hand, then instead of going for point-biserial correlation, it is advisable to use the biserial correlation coefficient. Whenever the research requires establishing relationship between two variables, one of which is continuous and the other is dichotomized by placing an arbitrary division, the biserial correlation is a suitable choice and a better choice as compared to point-biserial correlation. So, the biserial correlation coefficient is useful in those situations when the data comprises of a continuous and other dichotomous variable with arbitrary division imposed on it. The data does not meet all the assumptions of Pearson's product moment correlation coefficient. The biserial correlation coefficient is also useful in item analysis of a test, that is item test correlation. However, there are certain situations where biserial correlation coefficient is not useful. Let us identify those situations also. The biserial R is not a very popular method as it is difficult to calculate when the data is not normal. That is, in such situation, the phi coefficient can be used, which is discussed in subsequent modules. The biserial R cannot be used in a regression equation. The biserial R cannot be used for comparing with other correlation coefficients as it goes beyond the range of +1 and -1. Let us look into the calculation formula for biserial correlation coefficient. The biserial correlation coefficient can be calculated using the following formula. Equation 3 gives the calculation formula for biserial correlation coefficient. R BIS is the symbol for correlation coefficient of biserial type. The formula is R bis is equal to MP minus MQ divided by sigma multiplied with PQ upon U. Let us understand what each symbol means here. MP is the mean of the group in category 1. MQ is the mean of the group in category 2. Sigma is the standard deviation of the group. P is the proportion of group in category 1. Q is the proportion of group in category 2. U is the height of the normal curve ordinate dividing the two paths P and Q. The calculation formula for biserial correlation coefficient. An alternative formula to calculate biserial R is also available. This is slightly convenient than the earlier one mentioned in equation 3. Let us have a look at the alternative formula for the biserial correlation as given in equation 4. R bis is equal to MP minus MT divided by sigma multiplied with P upon U. We know what each symbol means as given in equation 3. MP is the mean for P, MT is the total mean, sigma is the standard deviation of the total, P is the proportion for category 1 and U is the height of the coordinate in the normal curve. The numerical application of biserial correlation. A school counselor wants to check out if a special training program she devised is related to performance in numerical ability test for students. Among the 145 students, 21 were randomly chosen to undergo the training program. The two groups were of 21 students with training and 124 was the other group without training. The scores obtained on numerical ability test by trained and non-trained students. Have a look at the columns. The trained group is the first category, the non-trained group is the second category and the scores have also been shown. The total is given in the fourth column. The sample size is given at the bottom and the means have been calculated as mean total to be 81.35, mean for category 1 to be calculated as 87, mean for Q, that is the second category, is calculated to be 80.39. The standard deviation for the group is 8.8. The proportion P is 21 upon 145 and Q is 0.855 as obtained by dividing by 124 by 145. The U or the height of the y coordinate in this case is 0.228. The value of U is obtained from the table that gives the height of the ordinates in the normal distribution of unit area with n equal to 1, mean equal to 0 and SD equal to 1. As evident and explained by figure, one can find U to be 0.228. Look at the figure. We find the P and the Q values and we locate the U and find that its value is 0.228 from the table. So, let us apply this data that we have in the table to calculation of biserial R. And as we remember, equation 3 and equation 4 both talk about calculation of biserial correlation using two different formula. On application of equation 3, we see that biserial R can be obtained as 87 minus 80.39 divided by 8.8 multiplied with 0.145 into 0.855 upon 0.228, which turns out to be 0.41. The same value of biserial correlation can also be obtained on application of equation 4, and the readers can check out for that. The significance of biserial R. The obtained value of biserial R can be put to test against the null hypothesis. The degree of freedom n-2 can be used to find the critical value of R from the table. If R calculated is more than the R critical, then it can be taken as significant and we reject the null hypothesis. The curvilinear relationship. Let us recall what we learned in module 22. The Pearson's product moment correlation is best suited to data that is linear in nature. Otherwise, errors may occur. The research data, however, is not linearly related always. When the straight line of fit is not apt enough to describe a set of data, it is said to be curvilinear, or more simply, a non-linear relationship. In such situations, Pearson's R is not an adequate measure of correlation. In such data, a curve rather than a line of best fit is used to describe the degree of relationship that the variables share. Fitting a curve instead of straight line would give a better and more accurate measure of correlation among the variables. One often encounters non-linearly related variables in data measured in ratio scale, psychophysics, etc. Figure describes the curvilinear relationship among the data. Have a look. Fitting a line of straight fit to this data is not doing justice to know about the relationship that the two variables share. However, if a curve is fitted to the data, then it may be more justified. The IBM SPSS 20 application to correlation. The IBM SPSS 20 cannot be used directly to calculate biserial correlation. So, the point biserial correlation coefficient is calculated and then the equation is adjusted to calculate the biserial correlation coefficient. Let us take the numerical example used in section 3.2 and apply the IBM SPSS 20 commands to it. The researcher wishes to explore if anxiety scores obtained during a task performance were related to the gender of the group being tested. The scores on anxiety test are continuous as obtained by the males and females, which is the dichotomous variable of gender is quoted as males 1 and females as 0. The commands that need to be given are analyze, descriptive statistics, frequencies. Summary. Many a times the research data does not conform to the assumptions of linearity and continuity and hence not suitable for Pearson's R. So, other measures of correlation have also been devised by statisticians. A point biserial coefficient is a special type of correlation coefficient that relates observed item responses to the total score. In the examples above, we see that both sets of data have a range of values example salary, a point-biserial coefficient is specifically used when one set of the data is dichotomous in nature. In this case, the score multiple choice items are the dichotomous data and they can take on values 1 for a correct response, 0 for an incorrect response. The calculation of a point-biserial coefficient is a bit simpler than that for a Pearson's coefficient, but the resulting coefficients and their meanings are the same. That is, a positive point-biserial coefficient would mean that high values on the dichotomous data, that is the correct item responses, are related to high values on the total test scores. We also call this coefficient as an item total correlation and is used for item analysis. A point-biserial coefficient computed for every multiple choice item is considered useful because it reflects how well an item is discriminating. A high point-biserial coefficient means that students selecting the correct responses are students with higher total scores, and students selecting incorrect responses to an item are associated with lower total score. Given this, an item can discriminate between low performing examinees and high performing examinees. This is a desirable characteristic of test question. Very low or negative point-biserial coefficient computed after field testing new items can help identify items that are flawed. There are limitations to using any statistic. For example, one major drawback in using the point-biserial coefficient is that it is sample dependent. Administering an item to different group of students may result in different values. The concept of biserial correlation coefficient is quite similar to the point-biserial correlation. The difference between the two pertains to the measurement of the categorical variable only. The dichotomy in the variable is not true but has an underlying continuity to it in biserial correlation. The biserial R cannot be used in regression equations and cannot be used for comparing with other correlation coefficients too, as the values range beyond +1 and -1. When the straight line of fit is not apt enough to describe a set of data, it is said to be curvilinear or more simply a non-linear relationship. In such situation, R is not an adequate measure of correlation.